In this video, we're going to talk about a theorem. The mean value theorem. What is this theorem? Let's take a look. We're going to start by considering the following graph. This graph right here. So we see we got a nice function. It's smooth, it's differentiable, it's continuous on the interval a to b. Okay, so we want to keep this graph in mind because we're about to ask a question about the graph. But first, notice and review that the average rate of change of this function above, f of x, over the interval a to b is, remember, well, it's just f of b minus f of a over b minus a. And that, of course, is the same as the slope of the secant line connecting the points a comma f of a and b comma f of b. So if we go to this graph right here and we just draw a line connecting the two endpoints here like so, that line right there has slope, right? Has slope equal to f of b minus f of a over b minus a, and that's the average rate of change of the function f over the interval a to b. So just refreshing our memory here, okay? Now, the question is there some value, say x is c, between a and b, such that the derivative of the function f at this location c is equal to this average rate of change here, f of b minus f of a over b minus a. So we think about what that means, right? Go back to the graph. Is there some number somewhere in this interval, call it x is c, such that when I go to that location, the instantaneous rate of change of the function, or the slope of the tangent line of the function at this location, is equal to the slope of that secant line connecting the endpoints as we see here in the diagram. What that would also mean is there a location for which the tangent line itself within this interval is going to be parallel to this particular secant line. So that's the question we're trying to ask, and we might just kind of look at it and go, there seems like there might be a place. Maybe right around there, if I drew a tangent line, seems to be there is some location here. Say x is equal to c, such that that is true. And in fact, that's what the mean value theorem is really getting at here. You look at this picture, and in fact, better lines than the one I drew right a moment ago, but there's actually two locations, right? In this case, here's some value of c, call it c1, and there's actually another location somewhere over here, call it c2. And so we can see that there are some values of c within the interval a to b such that this is true, and that is the instantaneous rate of change of the function is equal to the average rate of change of the function. So when will this be true is the question. Does it always happen? Well, we happen to have a nice continuous function in this situation and also differentiable. So perhaps these conditions are necessary. And in fact, mean value theorem tells us, assuming that the function is indeed continuous on the closed interval a to b, but also differentiable on the open interval a to b, assuming that that's true, then there has to exist at least one value, maybe more, of x, say, equal to c within the interior in the interval a to b, so that the derivative at that location is equal to the average rate of change of the function over the interval. And that's why we call it the mean value theorem, not because it's a big meanie. No, mean meaning average here in that sense. And that is, you take a nice continuous and differentiable function over an interval, and you find its average rate of change, then there will always exist some number x equal to c within the interior of the interval of x's, such that this will be true, and that is the slope of the tangent line at this location of x is equal to c is the same as the slope of the secant line over the entire interval. Now, we're not going to prove this theorem in this video, but you can hopefully get the idea of why this might be true by looking at the example. There's a special case of this theorem called Rolle's theorem, special case of the mean value theorem here. And basically, as long as all the conditions are met, so all the conditions are met for the mean value theorem, except the only difference is the values of the function at the endpoints a and b are the same value. So in that special case, then the slope of the secant line connecting the endpoints will be equal to 0, and there must exist at least one value x is equal to c within the interval such that the instantaneous rate of change at that location is equal to 0. So really special case here, and just to see a picture of what Rolle's theorem is telling us, a picture like so, right? So you can see this particular function y is equal to f of x. Maybe this left-hand endpoint is a, right-hand endpoint is b, and we can see that in this picture, f of a is equal to f of b, and so that tells us that the average rate of change, f of b minus f of a over b minus a, is going to be equal to 0, right? Just draw that secant line connecting these 2 points. Slope of that secant line is equal to 0, and in fact, that location for which the slope of the tangent line is equal to that is located right up there at the vertex of this particular quadratic-looking function. We'll just assume it's quadratic. Right up there, right? There is our C location within the interval, and at that location, f prime of C is equal to 0. So it's just a special case, but we often like to talk about that because it does give us potential of local extrema. So that's what the theorem is telling us. Let's look at an example of this. Here is a function right here, f of x is equal to x divided by x plus 2. And assume, for the sake of this situation, that it is defined over the interval right here, the closed interval -1 to 2. Question, does there exist some value of x within the interval such that the function's derivative at this location of x is equal to this quotient right here, f of 2 minus f of -1 divided by 3. Now, first of all, note that's the same thing as f of 2 minus f of -1 over 2 minus a minus 1. So really what we're asking here is, does there exist some value of x within the interior of this interval so that the function's derivative is equal to its average rate of change over this particular interval? So the question is, does there exist this value? And if so, we would like to find the value, or maybe there's more than one value. Take note, this function, f of x as we have x over x plus 2, the function f of x is continuous on the interval -1 to 2. Now, it's not continuous for all real numbers. It's definitely not defined at x is equal to -2, but because that's not part of our interval, we're good on that. We're continuous over the closed interval. It's also differentiable on the interval, open interval, -1 to 2. This is a rational function here, and we know it's defined over this particular interval, and because of what we know about the behavior of this particular function, it is differentiable on this interval as well. And so what that tells us is MVT, if you will, the mean value theorem, applies. And because it applies, it also tells us that indeed, yes, there exists such an x value that we're looking for, the same x that's satisfying that condition right above. And so there's got to be at least one x. Maybe there's more. We'll have to take a look. But now that we know there's got to be one, let's go ahead and find this particular x or x values. So the first thing we got to do is, of course, figure out what that average rate of change actually is equal to. So our function, let's just write it here. So it's on the screen. Remember right above, it is x over x plus 2. That's our function f of x. So what is f of 2? F of 2 is equal to 2 over 2 plus 2, 2 over 4, that's a half. F of negative 1 is going to be negative 1 over negative 1 plus 2, which is negative 1 over 1, which is negative 1. And therefore, the average rate of change of this function over the interval from negative 1 to 2, which is f of 2 minus f of negative 1 divided by 3, is going to be f of 2 is a half minus f of negative 1, which is a negative 1, all over 3. And notice 1 half plus 1 is 1 half plus 2 over 2, all over 3. So that's going to be equal to 3 over 6, which is equal to a half in this case. So the average rate of change of this particular function over this interval is equal to 1/2. So then what do? We got to find the derivative here, right? So the derivative of this function is needed in order to figure out what value of x this occurs at. So let's go ahead and find the derivative. F prime of x in this particular case is going to be, well, we could choose to turn this to a product or a quotient. Let's just do quotient rule for fun. It's going to be the denominator x plus 2 times the derivative of x in the numerator, which is just a 1, minus my x times the derivative of the denominator, which is a 1, all over x plus 2, quantity squared. What's that give us? An x plus 2 minus an x over an x plus 2 quantity squared, which is a 2 over an x plus 2 quantity squared. And remember, we're setting this equal to the average rate of change of the function over the interval, so equal to 1/2. So now we have to solve that particular equation, which is the same as if I divide both sides by 2, a 1 over an x plus 2 squared equal to a 4th, or equivalently, 4 is equal to x plus 2 squared. Go ahead and root both sides, giving me plus or minus 2 is equal to x plus 2, or notice we get plus or minus 2. Minus a 2 is equal to x. So what two values is that? Well, it's 2 minus 2, so x is equal to either 0 or it's equal to negative 4. We are going to discard the negative 4 since negative 4 is not part of the interval negative 1 to 2, and thus this location for which it must occur is at the location of x is 0, which is on the interior of this interval negative 1 to 2. And as mean value theorem had guaranteed, there does exist such an x in this particular case. Here's a picture of that situation. Here is the graph of x divided by x plus 2 over the interval from negative 1 to 2. And the green line there is showing us that we have this average rate of change, the slope of the secant line, right? That line right there has slope equal to 1/2. And as we can see at x is 0 right here, the slope of the tangent line at that location is the same thing, also has slope equal to 1/2. So that's showing us that f prime of 0 here is equal to a half. And mean value theorem helps us out. So mean value theorem is helpful a lot in theoretical mathematics in proving or disproving other statements, but of course it is also an application of using the derivative here to find other things. And so that's it for the mean value theorem video. Kind of a neat video, and until the next one, it's over now. It's Matt and Beats, and I'm out of here.